This one?
Yeah, that's good.
Yeah. So we'll go view full screen. Sure. Is it okay?
Yeah.
So next speaker, Wang from Northwestern University.
Ooh.
We'll talk about, sorry, I think I...
It's okay. I got it.
Oh, sorry.
It's okay. We figured it out.
Yeah, so talking about the lesson from combining high contrast imaging and high resolution spectroscopy, 7 years of reflection.
Yes, it is indeed reflection, because just last month we decommissioned KPIC. So this is going to be 7 years of on-sky lessons learned from doing an experiment where we combine high contrast imaging and high resolution spectroscopy. First, I just acknowledge I'm presenting this on behalf of the KPIC team, which is quite a large team. It's PI'd by our fearless conference organizer, Dimitri Maoué, co-PI Nem Jovanovic, and I'm the project scientist. But you can see there's a whole group of people, especially many early career folks that all lent their time and effort to make KPIC possible and happen. So just want to acknowledge that this is really a team effort, and I'm just presenting the results from the team. So what exactly is KPIC? KPIC was this idea that what if we fed the light from the KEC2 facility adaptive optics system, and can I do this? So going through the deformable mirrors, and what if we steer that light into a single mode fiber, which then connects into the NIRSpec high resolution spectrograph. If we could do this and put the fiber on a planet, we can get near infrared spectroscopy of exoplanets at very high spectral resolution. We're talking R of 35,000. For most of the talk, I'll be talking about KPIC's K-band capabilities. That's what we really honed in and did science with, but we also technically have J, H, and L-band capabilities as well, or had, RIP. So this is how KPIC observes. So here's an image of a star, a well-known star, harbors 4 giant planets orbiting between 50 and 70 AU with masses between 5 and 9 Jupiter masses. I wonder which one system we're talking about. So we have 4 fibers, and we place one of our fibers at this particular location offset from the star. And we have to trust that if we integrate there for about 4 hours, we will get a spectral trace that looks like the one on the right, and that one has a spectrum of the planet. One of our first experiments was, can we do this? Can we put the fiber at this precise location with an unseen planet and actually place it with enough precision that we're getting enough planet light to detect all these absorption lines in a planet spectrum? So this is how we do it. So here on the left, this is kind of a cartoon of our tracking camera. Our tracking camera operates in H-band. We're observing in K-band for our science. We know the location of our fibers relative to the tracking camera. We calibrate that in the daytime. So what we have to do when we observe a planet like HRA 799 is we have to put the star at this particular location on the tracking camera such that in H-band it's here, but due to atmospheric refraction, and K-band is actually in this unseen position, which is blindly offset from the location of the unseen companion, which we know from orbit fitting that the companion is located right here. And getting this all right was something that we were concerned about going into KPIC, but this turned out to be as hard as we thought it was going to be, which is not something we can often say in high contrast imaging. It turns out that we can position a single mode fiber to within 10 milliarc seconds, and this is kind of the sweet spot, because if we're 10 milliarc seconds offset from the star in K-band, that only corresponds to a loss in fiber coupling of about 10%. So we're really getting at least 90% of the light of the planet into the fiber at all times, which is exactly what we're looking for. Another thing that we showed with KPIC is that we're looking at the tracking camera. The tracking camera is in a different focal plane than the fiber. There are non-common path aberrations, and we can show that just by looking at the total integrated flux through the fiber, we can actually perform sense the non-common path aberrations and correct for them to maximize fiber coupling. And this is some work led by Dan Echeverry and others in the KPIC team that really, we made this routine that every day we're observing with KPIC, there's automated routines that we sense the first X Zernike modes through the fiber and correct for that and maximize planet throughput. And maximizing planet throughput turns out to be one of the most important things, which I'll talk about in a bit. What's my next slide? Okay, yeah. So once we do, blindly integrate on the planet for about 4 hours, this is kind of the spectrum that we get. And black is the data. And just like JB mentioned, we're using the same techniques for NIRSpec We're doing it here. We're spectrally disentangling the light of the planet from the light of the star. We know that the planet light, or the planet model in red, has particular molecular absorption lines like carbon monoxide that you can see here that are spectrally distinct from the stellar spectrum that's in blue. And because of this, we can fit for what component of the total light is from the star and what component is from the planet. This works well when your planet light, where your starlight is relatively featureless. It only has telluric lines. But one of the things we learned is that there are things like correlated noise in your spectra. And one of the unanticipated sources of correlated noise was this thing we call fringing all the time. But what happens is that when you combine a high contrast imaging system with a high resolution spectrograph, is that with high contrast imaging systems, we love sensing the wavefront. We love splitting off a little bit of the light, sending it to some wavefront sensor, doing some correction. And every time we're splitting off the light, we're using dichroics, which are probably the least interesting thing in any optical design. But these plane parallel dichroics are essentially Fabry-Perot cavities. And basically, it will cause different wavelengths of light to either constructively or destructively interfere with each other. So basically, at some wavelengths, you get a higher intensity. At some wavelengths, you have a lower intensity. And it turns out for the kind of dichroic material with the particular index of refractions that we use and the thicknesses that we use, this spectral frequency of this ringing term happens to be basically the exact same spectral frequency that our planet molecular absorption lines look like. So basically, this ringing term from the star hides potential planet absorption lines and decreases our sensitivity to planets. And this is particularly bad because you're like, oh, let's just observe a calibrator star and calibrate it out. Well, the problem with KPIC is that so basically here's our tracking camera. And right before the tracking camera, we have a dichroic that splits the beam. So some of the light, the H-band light goes to the tracking camera. The K-band light goes into our single mode fiber. And to offset the field so that sometimes we're observing the star and sometimes we're observing the planet, we have a tip tilt mirror right here. So the tip tilt mirror controls the angle of the beam as it goes into the dichroic. If you look at the equation for how does the Fabry-Perot cavity cause the transmission to change as a function of wavelengths, you'll notice that there's this cosine theta term that's essentially the angle of incidence onto your dichroic plane parallel surface. And because when we look at the planet and we look at the star, that angle of incidence changes. Because of that, the spectral frequency changes, and you can see that when we look at the location of a planet versus looking at the location of the star, the actual spectral fringing is different. So we can't use a calibrator star or even the host star to calibrate out the fringing when we're observing a planet. And because of this, this is one of the major things we ran into in terms of our sensitivity. However, we managed to first analytically measure and fit this, and then B, wedge all our dichroics later on so that this no longer became an issue. So with this combination, we were able to identify and actually mitigate this unanticipated effect that we didn't think about going in when building KPIC. But this is one of the reasons why we did it, is finding these things that we may have missed when we are conceptualizing these extreme high contrast imaging, high resolution spectroscopy systems. With that, after we fixed fringing, we were able to build a KPIC contrast curve. So here is the flux ratio as a function of separation. The black dashed line, that's how much starlight leaks into our fiber as a function of separation. And then the blue line is if you do cross correlation and filter how much starlight could we filter out, how faint of a signal could we detect as a function of separation. And you can see that we're filtering out we have a CCF gain about a factor of 100. We can filter out about a factor of 100 times brighter stellar signal to see a faint planet signal. And in fact, within about 500 milliarc seconds, we're within a factor of 2 of the photon noise limit for KPIC. So we're achieving near the fundamental limit of what we can with the design of KPIC. Here, this is where we realize that throughput is really important for these high-resolution spectrograph systems. If you're in the background limit regime at these very large separations, your signal to noise goes as the flux of the planet over the square root of your background flux. And so if you can maximize the throughput of your planet, you maximize signal to noise. That's the best thing you can do. So improving throughput is the most important thing in your background limited regime. In the contrast limited regime, where you're limited by the stellar photon noise, specifically when you're limited by the stellar photon noise, then your signal to noise goes as your planet flux divided by the square root of your stellar speckle flux. And here, doing things like speckle nulling, which we demonstrated, Yinzi demonstrated on KPIC, does help you because that decreases speckle flux, and that it decreases by the square root of how much speckle light you can suppress with things like speckle nulling. But also, again, increasing throughput will also give you a corresponding square root gain because when you increase throughput, say by a factor of 2, your planet light increases by a factor of 2, your speckle light increases by a factor of 2, but your signal to noise, again, increases by a square root of factor of 2. So in both cases, end-to-end throughput really matters, and we spend a lot of time, if you ever hear about the KPIC team talking about end-to-end throughput all the time, this is why we talk about end-to-end throughput. KPIC has detected over 30 plus substellar companions. These are planets and brown dwarfs. Caitlin will have a talk later about the radial velocity survey. I just want to highlight 3 posters. Ben Zappi has a poster on detecting isotopologues in a brown dwarf. Juliet has a poster on measuring the composition of one of these new Gaia particles discovered planets. And Dino also has a poster on the bifurcation and spin speeds between giant planets and brown dwarfs, that giant planets spin faster. So check these out later in the week. I just want to mention one kind of lesson learned from high-resolution spectroscopy on the science side is that when you go to very high spectral resolution, you can resolve the cores of these molecular absorption lines. And if you look at, if you look at where the cores are formed, the cores of these lines are formed high up in the planet's atmosphere, much higher than the cloud deck. So here you can see on the right, this is a 2 plots put into one, so a little confusing. On the y-axis is pressure, so higher up is further up in the atmosphere, lower down is deeper in the atmosphere. And on the x-axis, the first one I want to pay attention to is the temperature curve. So this blue curve tells you the temperature-pressure profile. And the clouds in these LT transition objects lie at about 10 bar pressures. And when you're just studying the continuum emission is also coming from near the cloud deck, coming from these 10 bar pressures. So the continuum emission is degenerate with your understanding of cloud properties. But if you go to higher spectral resolution, you start seeing the cores of these lines, and these cores of these lines are formed high up in the planet's atmosphere, above the cloud deck. So you're able to measure things like, you can trace things like composition and disentangle them from the clouds. And here you can see in these corner plots where Jerry Xuan showed for this object that no matter what we assume about the clouds, even assuming no clouds, we're able to measure the same carbon to oxygen ratio and carbon to hydrogen ratio for the system. All right. I just want to acknowledge that it's been a great run. We started out building KPIC, and this is the first on-sky measurement of a spectrum we obtained with KPIC. It had such low throughput; it was like observing M dwarf with a 1 meter telescope. But we got that spectrum, and then we recently, just last month, decommissioned KPIC. You can see Nem is very sad. Dan is happy that he doesn't have to debug KPIC anymore. And I just want to highlight this has been an amazing team to work with, and we still have lots of science results still to come, so stay tuned. And HiSpec is coming up to Keck later on as well. Thanks.
So yeah, you said 10 millisecond positioning of the fiber is about 10% loss in fiber coupling into the fiber.
Yeah.
But that's the loss, right? What's the actual coupling when the stride ratio is at its best?
We don't think about that because that's like an intermediate term. What we think about at the end is end-to-end throughput, like how much planet light makes it all the way to the detector. And in our best case is 5%. So we throw 95% of the light away, but we get about 5% in the end.
And quick follow-up question: could you tell us again what were the big gray areas in your plot?
Oh, KPIC is a single-mode fiber instrument, so you can't really make a contrast curve from one observation. This is a compilation of all the sensitivity curves from KPIC together.
Kent Wallace, JPL. I was a little bit disappointed to hear that the dichroic is the least interesting optic in the
Well,
system.
Ken, you know what my favorite optic is? The atmospheric dispersion corrector.
Oh, be still my beating heart. Were there any other sources of fringing other than that dichroic, Jason, that you had to address?
There's also the NIRSpec entrance window, the entrance window to the cooler, but that one is static, so that one's easy to fit for. It's these dynamic terms that change as a function of fiber positioning that are really the hard ones.